I would like to also thank a few people in the beginning, and at first I would like to thank the organizers, who are wonderful, wonderful young researchers and a real pleasure to work with. Secondly, I would like to thank, maybe I'll go into a little historical anecdote to explain why I'm thanking that particular person, actually. So it was maybe 18 years now, it's scary to say, ago, and it was at Berkeley. I got a call from Professor Alex Pines, a professor in chemistry, and then his postdoctoral researcher, Andreas Trabesinger. And they said, we hear you are working on optical magnetometers, and we feel that we need to talk. Why don't you come over? So I came over to Alex's office, and there was Andreas. And these guys had quite a strange proposition to me. They said, we feel we need to measure nuclear magnetic resonance with optical photons. I said, sure, well, why not? But what motivates you? And then they provided some motivation that only that sounded a little bit strange to me at the time, but eventually grew upon me. Anyway, that phone call sort of brought me into this fascinating field of zero field NMR, and for many years I felt that we are working on sort of a fringe of the fringes there, nevertheless. Over the years, as more and more work was done by a lot of wonderful people, many of them are speakers here, like Thomas Theis and Szymon Pustelny and all the others. There's sort of a bulk of results has accumulated, and this became no longer a fringe. And then there was one event that happened that really basically brought this whole field into mainstream. And what it was in fact another conversation with Andreas Trabesinger, who said, look, there is this program, Marie Curie ITN program, and I think one should establish one in the field of ZULF NMR. And I confess I had a lot of resistance initially, because I heard from colleagues that there is a lot of sort of administrative overhead to run this program. But eventually Andreas convinced me that this is a good thing to do, and then we both went out and recruited Szymon Pustelny to actually lead this collaboration. And what happened next, you know. And now I think the fact that there is a dozen of young, wonderful, and motivated people working in this field ensures that it will never die, basically. So I'm completely shocked and surprised that this thing used to be a deep fringe of NMR, and now it is a mainstream NMR and will never die. So I'm super happy, and I would like to thank Andreas Trabesinger for playing sort of a key role in this whole story. Anyway, so these are my thanks. Now those are out of the way. I would like to sort of continue on the theme that Szymon has started and tell you about another type of sensor that can be used to detect zero and ultra low field NMR, and this is a sensor based on nitrogen-vacancy center in diamond. And I would like to say that this talk is not at all aimed at experts like our chairperson. So I doubt Anjusha will learn anything that she doesn't already know much better than I from this talk, but it's actually geared at people who are still wondering what is an NV magnetometer, how it works, and I hope to address that here. So we start from the very beginning, you know, there is a diamond that used in jewelry, and it looks beautiful. Look at all this color play there in this beautiful stone. Now, this is a natural diamond, and these days there are technologies, and if you ask me later, I can tell you a little bit about how diamonds are produced. But the point is that you can produce fairly big chunks of diamond that is extremely pure, with maybe parts per billion of any kind of impurities in it, and moreover, which is the entire thing is a single crystal. And nowadays we typically work with samples that are maybe, you know, half a centimeter on the side and maybe a millimeter thick, something like this. And what you can see here is that if you take this ultra pure artificial diamond and just look at it, it's extremely boring compared to this, you see? And the reason for this is actually that it is pure. It turns out that this the color play of the diamond is due to the fact that there are defects in the diamond. And I think it is actually a very sort of philosophical thought that beauty comes from defects and not from perfection. Yeah, but anyway, one of these color centers that is of most interest to us is so-called nitrogen-vacancy center. And you all know that diamond is a carbon lattice, as you can see here. And in a nitrogen vacancy center is when you take two adjacent carbon atoms and you remove them from the lattice. And then you take a nitrogen atom and you put it in place of one of the carbon atoms that you have removed. And the other vacancy you leave as a vacancy. Okay, and so now you have this thing which you can think of as a sort of a molecule in the vacuum, if you like, of these carbon atoms in the crystal. And so this is the center of interest to us, because, and I will explain why. In short, it has an amazing combination of properties that turn out to be very good for magnetometry. So there are all kinds of details. The first detail I'm going to tell you is that there are different charge states that this molecule can be in. And the charge state that is interesting from the point of view of magnetometry is when the whole thing is singly negatively charged. So there's one excess charge on it. And the question is, how can this happen? Well, the crystal usually has some other impurities. Typically, it's just what's called a substitutional nitrogen without the vacancy. And such an impurity can be a donor of electron. It donates an electron, then it migrates in the crystal and ends up on the nitrogen vacancy center, and that's how it becomes NV minus. Now, I would like to, people sometimes are scared that it's a very complex system, and in the end, when you really dig deep into it or try to have a PhD on the topic, it is full of details and complications, but in fact, you can start with something extremely simple, and I call it primitive NV magnetometry. And actually, when we started in this field, I think it was about 2008. So one of the first experiments that was done was, in fact, you can see here. So this is a laser pointer, and old-style laser pointer. This is a napkin. And this is one of these diamonds. I think this one was 3 by 3 by 0.5 millimeter diamond. And now I showed you before a very, very pure diamond that has very few impurities. This one is a crystal that we've specially prepared to have as many of these nitrogen vacancy centers as possible. And so it is actually no longer translucent. It's actually, it looks kind of dark red, or it looks that sort of blackish, I would say even. But if, when you shine the green light on it, then you can see that it fluoresces with a red color. Okay, and what is going on? It's already interesting physics here. So a diamond color center, it has electronic energy levels, and this is the ground electronic energy level, and this is an excited electronic energy level. But it's in a crystal, and in a crystal you have in addition to just like in a molecule, if you want, in addition to electronic states, you also have vibrational states. And in general, you can have these vibrations. So if the center is in the ground state, there can be vibrations, and they could add energy to each of the electronic states. Okay, so it's in the ground state, there are some vibrational states, and then the excited states. And actually, in molecular spectroscopy, when molecules are free, you can have sort of distinct lines corresponding to vibrations and even rotations. But what happens here is that the density of these lines is so high that the adjacent lines are closer than the spacing between the lines. And so we no longer talk about lines, we talk about bands. So we have sort of this vibronic band, as we say, here and there. Now, the energy scale here is that the room temperature is a very small energy here. It's so basically all the centers, color centers in this crystal, they live very close to the bottom, very close to the ground vibronic state here. And now when we shine the green light, it turns out that it is above this energy here between the bottom and the bottom here. This is, by the way, called zero phonon line, okay? But the green energy is higher. And so what happens is that we excite the center, and we excite an electronic excitation and a whole bunch of vibrational excitations, and we end up here. And what happens after this, it turns out that very, very quickly on a picosecond time scale, there is relaxation without emission of any photons, and the center falls back to the not back, falls to the bottom of this band. And the lifetime of this state is sort of typical atomic or molecular lifetime, something like 10 nanoseconds or so. And then there occurs an emission. And when the emission occurs, you can also excite, once again, some vibrations in the ground state. And the result of this is that the absorption spectrum is peaked here in the green, and the emission spectrum is peaked, you see, at a smaller energy. It means this is the color that's to the red from the green, and that's what happens here. So the scientific term is the Stokes shift, and you excite with the green, and then the light is Stokes shifted for emission, and then you see the reddish or even infrared emission. By the way, if you have questions, please ask. I'll be very, very happy if you do. Right. Okay, but this is not yet magnetometry. This is just basic physics of color centers. So in order to see how magnetometry works, we need to take a magnet and start waving it around our sophisticated apparatus here. And when we wave it around, we will find that the intensity of the emitted light actually depends on the magnet. And we can do sort of more or less careful experiment, align our magnetic field with certain axes in the crystal, if you like. Those are details, but here is what you see. This is basically the experiment I showed you here, but sort of presented in a more scientific way. So what you have here now is the strength of the magnetic field, and here you can see the dependence of the intensity of the emitted luminescence as a function of magnetic field. And so what you see with your naked eye as a change in the intensity of the fluorescence as you wave the magnet around the diamond is sort of this initial slope. You see that there is several percent of change in the intensity, and then with your instruments you can actually see these sharp lines, the physics of which is largely understood. It's actually a rich physics, and it has to do with different kinds of physics for different features here, and I'm not going to go into that because it's sort of slightly more advanced than this introductory talk that I'd like to give here. But the point is that there are various line and level crossings, and they produce sharp features here. And what you can do is you can take advantage of these sharp features and say bias your magnetic field to one of these points, and then use the steep slope of the dependence of the signal on the magnetic field to do sensitive magnetometry. And this is done. So one of these features here is what's called ground state level anti-crossing, and maybe I'll explain the energy levels a little bit later. All right. Now, one thing you can notice is that these sharp features, they are sort of absorptive. So if you tune to the peak of the feature, you have only quadratic dependence on the magnetic field. But of course, it's easy to convert these absorptive features into dispersive features, and this is done with a magnet. So you put a diamond here, and you can put a little electromagnet and add a little bit of a modulation of your field, and then have a lock-in detection, and then you convert these absorptive features into these dispersive features like this. And so you can build a magnetometer, and we started playing these games several years ago, and it's part of the PhD thesis of Huizia Zhang. She's about to defend it. And eventually these things can be made fairly sensitive, for example, around a few, maybe 10 nowadays, maybe 10 to 20 picotesla per root hertz, and this starts to get in the range where you can start thinking about detecting, basically replacing the atomic magnetometers that Shimon talked about for detection of ZULF NMR. So this is the energy level diagram without the vibronic bands, and it turns out that so the ground state of the nitrogen vacancy center is a triplet, and it means that it's a spin 1, electronic spin 1 state, and the crystal symmetry tells you that in the absence of external field, the M plus minus 1 states are degenerate, and m equal to 0 state is split, and it turns out that the splitting is on about 3 gigahertz or so. And if you apply a magnetic field, there is a linear Zeeman effect that splits the m plus minus 2 in proportion to the applied magnetic field. The excited state also happens to be a triplet state. But in addition to triplets, it turns out there is a system of singlets, and this sort of structure plays a very important role in the physics of NV centers here, because it turns out that in contrast to, let's say, an atomic system that requires you to think a little bit if you want to polarize it somehow. Here you just shine the light that is of shorter frequency than the zero phonon line. For example, we like to use the green light, and the centers with very high efficiency all polarize here into the m equal to 0 state, independently of the polarization of the light. So it's very different, and in some sense it's easy. So now we can initiate this state. We can also the other important thing is that the lifetimes are fairly long on the solid state scales, so to say, then we have sensitivity to magnetic fields, first order sensitivity to magnetic fields, and then we can also use the same effect related to the singlet state to read out, because if you are already polarized in this m equal to 0 state and you shine the green light, the centers tend to cycle back and forth here, and you see a lot of fluorescence. And if you somehow make a transition to one of these plus or minus 1 sublevels, and you excite to the excited state, then for this m plus minus 1, there is a high probability of inter-system crossing, and the centers hide for a while, for several hundred nanoseconds, in the singlet multiplet. And while they are hiding there, they are not participating in fluorescence. So here people talk about a bright state and a dark state, although the meaning of it is quite different from what we usually say in atomic magnetometry, like for instance in Schimon's talk just now. So the bottom line is that we can initialize and we can probe, and there are long lifetimes, and the system is sensitive to fields. It's wonderful. All the ingredients for the magnetic sensor. And now, of course, our interest is in ZULF NMR. You may recognize this picture. It appeared already in Thomas Theis's talk, and we had an ITN meeting at Mainz last year. And you know the funny thing about this picture? March 2019, and nobody is wearing masks, huh? There was a time. Okay. So one thing about this magnetometer based on nitrogen vacancy centers is that actually it turns out that it can measure magnetic fields, but not at zero field, unfortunately. And I will show you a little bit later the reason for this. And so if you want to do ZULF NMR, you need to learn to do zero field magnetometry with nitrogen vacancy centers. And we recently actually learned to do this, and there was this paper that you see here. Right. So the trick here, and maybe I should tell you that something I guess I failed to tell you in the right time. So let me back up here. So I need to add one more component to tell you how this magnetometer works. So there is if there is a magnetic field applied, these levels are linearly split as a function of magnetic field. What's going on? And so what you can do is you can measure the energy splitting between m equal to 0, that is independent of the field for a field parallel to the axis of the center, to one of these sublevels. And how do we do it? We apply a microwave. We apply a so the centers are initialized here. Then we apply a microwave field. If it's on resonant, we drive some of the centers to one of these sublevels, and then with the light we drive it up. And after this, it goes to the singlets, and so we detect whether we have a resonance here or not by observing the brightness. It's called optically detected magnetic resonance. So basically, the common magnetometers, which are slightly more sophisticated than those microwave free that I described in the beginning, they actually use microwaves to drive these transitions. And normally we just have a wire through which we drive the AC current, and we don't really care very much about the polarization of these microwaves, and it turns to be linear most of the time. And that is not good for zero field measurements. So it turns out that there is a key device, which is a very, very simple thing in the end. It's a device to produce circularly polarized microwaves, and in fact, our Polish colleagues, Professor Gawlik in particular, have mastered this technique, and they even sent us some of these boards that we used initially. And the idea here is the following: that you have two wires, and if you run a current through the wire, there is a magnetic field that is the shape. It goes around the wire, and if you have two of these wires and two independent currents, you can choose a point above the two wires, and this will be somewhere here. So you have one of these fields oscillating in one phase, and another one is shifted by about pi/2, and so out of these you can, out of two linearly polarized microwaves, you form basically a rotating magnetic field, and that actually enables the magnetometry at zero field. So finally, I can explain to you. Why zero field magnetometry is normally a problem. So here, what you have is a magnetic field, and here you have the resonance frequency for the transitions, and here you see what they are. And by the way, the reason you see such a complicated picture is because there is also a nuclear spin of the nitrogen, which is most of the nitrogens are spin 1. It's N14, and so what you have actually at zero field is that you have a series of resonances that have decreasing frequency with magnetic field, and another series of resonances where the field is increasing. And so if you are sitting exactly at zero field, you would have only a quadratic dependence, because you have something that depends one way, and another thing that's just like that depends the other way. And so you can see this in this symmetric pattern of the lines. But if you now, instead of linearly polarized microwaves, if you apply circularly polarized microwaves, you can see that you can break this symmetry completely, and in fact acquire a zero field sensitivity to magnetic fields at zero field. And so this is demonstrated in this paper for an ensemble magnetometer. So you can see that, you know, you turn off half of the lines if you go circularly polarized one way or circularly polarized the other way. So that problem is solved. And the application, in addition to zero of an ultra-low field NMR, could be measuring magnetic fields in shielded rooms, which is important, for example, for measuring small biological magnetic fields. And also there are some other applications. For instance, if you are trying to study some condensed matter systems like surface topological states that could be very sensitive to magnetic field, it could be good to have this device working at zero field. Now that was for an ensemble, and then the question is, does it work for a single NV center? And in fact it does, and we're just preparing a paper in collaboration with Professor Bala Subramanian, and these are the guys from our group. And it does work. You see very similar pictures here for a single nitrogen vacancy center. But can you guys hear me, by the way, or am I talking to?
Yeah, okay. We can hear you.
So thank you. Yeah, good. All right. Actually, why are we interested in doing zero field magnetometry with single centers? Because it's a part of a program that was conceived several years ago. And it's a very close collaboration between the Ulm group, in particular Professor Fedor Zhelesko there, and our group. And the essence of this concept can be sort of crystallized in that it's an extreme NMR. Why is it extreme? Because we want to measure basically NMR of a single molecule. That has been done already by others. We want to do it with a single nitrogen vacancy center with a single spin sensor. This also has been done by others. And we want to do it at zero field. That hasn't been done yet, and that's what we are trying to do. But this is like a completely extreme. So everything is a single spin, single sensor, and zero field. That would be very, very cool. And I'll talk a little bit more about this later if I have time. So in order to realize this, we started building a single NV center machine, and you know this is significantly actually more complex machinery than working with ensembles with many nitrogen vacancy centers. And so the help from these guys was, or I should say, has been very, very important. But we have now a working setup at Mainz, and this is actually already a few years old. So it starts by taking a diamond with very low densities of nitrogen vacancy centers, and then you shine the green light, and then you see some bright spots, and you think that one such bright spot could be a single nitrogen vacancy center, but you have to check, because sometimes it's a cluster and it could still look like a spot. So you do this intensity interferometry, or in the quantum optics language, you measure the G2 autocorrelation function of these emitters. And if it is actually a single emitter, you should see strong anti-bunching. And that's how we check that these are single MVs.
Dima,
yes?
We have a question. So how far would the sample be to this NV center in the case of a single NV?
Yeah, so in principle, it is determined by how close to the surface of the diamond you can have this nitrogen vacancy center, and this is one of the focal points of the research of the NV diamond communities to prepare centers that are very shallow and still maintain these good properties that I talked about, large relaxation time and ability to emit photons. And currently, I think the shallowest nitrogen vacancy centers that people use are about 4 nanometers. There are some reports of maybe 3 nanometers or something, but then their properties rapidly deteriorate if they are shallower. And then you can put the sample right on the surface, so you're talking a few nanometers in the end. So it's really atomic resolution in some sense, yeah.
Okay, thank you, Dima.
Yeah. it's funny that you asked this question, Anjusha, because
I know a question.
You are an expert.
No, and also John has question. What does all that jargon mean?
Oh, that's jargon. Okay. Sorry. Yes. I was just. Thank you, John. I was just going to say that if well, I can. Am I running out of time, or I have a lot of time?
Your time is actually up. You can talk till 5 p.m. 5 more minutes.
Okay. Yes, maybe we'll come back to this, but just maybe I will just say that the quantum that the sort of if it, in simple language, if you have an ensemble of emitters that emit independently, then you actually tend to have clustering or bunching of these fluorescence photons. And if you have a single emitter, you have an anti-bunching. It means that if an emitter has emitted a photon, it cannot emit another one immediately because it has to think about it and then emit another one. I can explain on a picture, but in scientific language, it's called that the G2 second order or intensity autocorrelation function should go to 0 ideally. Thanks for the question, John. All right. Moving on, I just want to say that I'm very excited to show you this picture because the data I received from these gentlemen who are PhD students in our group I think Omkar is actually an undergraduate student. Til is a PhD student, and Omkar is an undergraduate student. Anyway, they sent it to me this morning, and I'm very excited to show this to you. So I must say that other groups have been seeing proton NMR with single NV centers now for several years. So this is not a big news in terms of sort of the community, but for our group, it is a very exciting thing. You can see that in fact you can do proton NMR. These are different fields that are applied, and there is some oil on top of the diamond, and you can actually see these. Well, you can say they are noisy, but we love them. They look like resonances, and there's a linearity that we can see here of the proton precession frequency, and the slope here corresponds exactly to proton gyromagnetic ratio. So this is now NMR of many spins and not at zero field, but it's a very important step for our experiments. So now just a few final remarks that I would like to make before I finish. If you think of NMR, you can split it into three important parts. So the first one is the polarized sample. The second one is encoding of useful information into the nuclear spins. And here there are two sort of big subclasses of NMR. One is imaging, where you want to say where the spins are. You more or less know what they are, but what type they are, but you just want to know where they are. Or there is spectroscopy, when you want to know what kind of environment the spins are in. And so here is where the useful information is sort of written into the spins. And then finally, you need to detect them. If you are interested in quantum computers, then you would notice immediately that, you would notice immediately that in quantum computers you have also similar stages: initialization, operation, and then readout. Now we are talking about zero field NMR. So as already was said by Thomas, I guess you need to figure out how to get rid of the need for magnetic field in the polarization stage, and then encoding, and then in readout, in each of the three stages. So when we are talking about this business with single NV centers and a small number of nuclei that you interrogate, there's a very, very beautiful technique which is called stochastic polarization, and this is my favorite technique because it involves doing nothing, and I really like to do nothing whenever I can. And the idea here is that if you just prepare n nuclear spins in random state, you will have for any direction an excess on the order of square root of n. You don't know what the whether the excess will be positive or negative, but you know that each time you do this, you will have this, and you can then use this noise to do your nuclear magnetic resonance experiments. And the nice thing about small numbers is that square root of 1 is equal to 1. So when you get to small numbers, your stochastic polarization or do nothing polarization is just as big as your best hyperpolarization. So this is one of the advantages of single NV. Okay, encoding and then detection. For encoding, you already heard that a zero field NMR, for instance, uses J couplings for spectroscopy, and for detection, we like to use atomic magnetometers, and also squids have been mentioned. But now the point of my talk was that you can also use diamond here. And I must say, by the way, that now this is sort of becoming relatively common. Here is, for example, a paper from a couple years ago, already from the group of Victor Acosta, where this is an ensemble NMR, but and on many spins, but nevertheless, small volumes have been analyzed here. So I don't have time to talk about it, but there is a big effort in the community, a very big effort in the community, to actually use diamond for hyperpolarization. And it turns out that it is relatively straightforward to polarize first of all, the nuclear spins of nitrogen, nitrogen-14 or nitrogen-15 inside the nitrogen vacancy centers, and also the spins of carbon-13 in the diamond crystal. And it's a little bit harder to figure out the ways to transfer this polarization out of the diamond, but even with hyperpolarized diamond, you can do things. And I must say that there is also a lot of thinking going on about how to use diamond also for encoding. And there is a variety of directions. So you can take nano diamonds and you can basically put them into biological systems, and you can study them if you want as your NMR agents. Or once again, people are trying to learn to transfer the nuclear polarization out of diamond into some kind of solution. So this is some developing area here. All right, so this brings me to the end, and I don't know if I overwhelm you with too much jargon, or was able to give you at least a flavor about the physics involved in NV magnetometry. I told you about this primitive magnetometry that we like to do, nevertheless, microwave-free magnetometry. Then about this development that allowed us to learn to do zero-field magnetometry. This is important for ZULF NMR. And finally, I spoke about the progress towards extreme NMR, where we will use a single spin sensor to study a single molecule at zero field. So this brings me really to the end. I thank you for your attention, and I'm super happy to answer questions.
Thank you, Dima, for that great lecture. So now, questions. Dima, we have one question from Michael. Dima, are you?
Yeah, I'm here.
Okay. What would be the application of a single spin, single NV system? I mean, single molecule.
Well, you wanted to put it to put ZULF NMR in a cell phone, and this will allow you to put it. I don't know what's smaller than a cell phone into your earphone or something like. But more seriously, I think you can look at, for instance, potentially very rare molecules. For example, molecules containing radioactive nuclei, or something really toxic that you don't want to have a lot of. In principle, everything, all the flavor is that everything is potentially cheap. Diamond actually is cheap, surprisingly, and no magnetic field is necessary, no prepolarization is necessary. So I think this is a good thing. And John here helps me out, as he normally does, that it could be the study of thin films. Yeah, thank you, John.